This is Brian Putt. Today I'm going to talk about different types of tornado diagrams and things you should be considering when preparing your tornado diagram. Look at primarily the difference between deterministic and probabilistic tornadoes. A typical tornado shows how a variable changes based on two values. These values reflect a low and high value for input variables. They tend to be 10 percentile and 90 percentile, but could be 5 or 95 or something else. But the range should reflect a variable and not a mathematical sensitivity, such as plus or minus 10%. This could be a quite small relative to the total range of the variable. The question becomes, what is the center line? In a deterministic tornado diagram, a specific value for a single evaluation. Oftentimes this is the mid value, the nominal P50, if you will, if you know what that is. Or most likely values if you're working with triangular PERT diagrams, PERT distributions. Or you may have a momentum case, something preferred by the management. The other alternative is a probabilistic tornado chart. The center line of the tornado is the mean of the value measure. So if you had a cumulative distribution function, and then you did a tornado diagram on the variables in that distribution, the center line would equal the mean of that CDF. Another consideration is whether the decision policy is going to change. If the value measure only contains uncertainties, discrete or continuous, there's really no decision policy. But if the evaluation had decisions, one or more, then we need to decide whether we want that decision policy to change when we change the variable. And this depends on when we learn or control a variable. Is it before or after an irrevocable decision? For example, once I start into front-end engineering or into FID, gathering information there probably can't change my decision. The ability to change the decision policy increases the spread because I could have two widely different alternatives I could follow with a different decision policy depending upon the outcome of the information. If the decision policy is embedded in the evaluation, such as in decision trees, the changing variable can change the decision policy. Ways to plot it. Well, the easiest way is to calculate the difference of the low and the high values from the center line. Thus, the tornado always has 0 as the center line. This can be sorted based on the swing, the high to low, such that it actually looks like a tornado. But this adds more effort and little information except tornadoes with many variables. You may wish to do that for the final report, if you will, but not for just evaluating your model and determining whether things are working right. Tornadoes can be very useful for that. If you expect a tornado for a variable to change the value and it doesn't, or if it changes in the opposite direction you anticipated, then you're going to want to investigate that. It's a little harder in my opinion, but plot the tornado using the actual value measures. It doesn't require taking the difference, but the center lines needs to be adjusted in the graph if the reference case changes. The endpoints are typically P10 and P90 or P5 and P95, as I've discussed previously. Let's talk about the advantages and disadvantages of the probabilistic. In favor of the probabilistic is the center line of the tornado matches the expected value of the value measure distribution. That'll become a question with your decision makers. If you show them one tornado with a center line of 11.5 and the cumulative distribution function has a mean value of 10, why is there a difference? In a probabilistic tornado diagram, it would reflect how the value measure expected value changes with the variables. You could even think of this as the value of control. In favor of the deterministic, it's typically easier to program using software, VB code, or manually. does not require then simulation, and requires changing the percentiles or values in a tree. So let's take an example. I've put together a very simple model that has 4 uncertainties, 4 random variables. One's a triangular, one's a discrete, one's an exponential, and one's a normal. And on the left, we see the deterministic, which has an EV of 7.96. And on the right, the differential. So you see the center line's at 0. The graphs, if they had the same range on the x-axis, would look identical as far as the length of the bars. But you can see there's very little difference in what's important and what isn't. The probabilistic shows more downside from the center line. So here on the left, we're seeing the deterministic, and on the right, the probabilistic. So we have more downside from the probabilistic. See how far this bar goes down. These are of the same scale, you'll notice. Showing the value measure can provide other information. The mean of the probabilistic is 11.01, shown over here, and is larger by 38% than the deterministic of 7.96. It also shows a more balanced sensitivity, whereas here you have a lot of upside. It would appear to be a lot of upside. It could be interpreted as upside. The exponential goes above 15 in both cases, but the discrete also goes above 15 in the probabilistic. If you were trying to keep things below 15, it tells you would need to work on both the discrete and the exponential. Now, something I've not seen other people do, but that could be useful, is you could take the standard deviation of the value measure, given that one of the variables is being controlled to the high side or the low side. And I was able to do that with Monte Carlo. It's a very unusual tornado diagram. And what it shows is that there's a lot of downside with the P90 discrete and a lot of downside with the P10 exponential. So this really differentiates. So once again, we'd have to work on these two things depending upon what our objective is. To better understand where those standard deviations come from, let's look at the S-curves for the low and the high for the two variables. We can see that the exponential, shown in orange, has a higher standard deviation than the blue, and that the lows have very little variation. So that's consistent with what we saw in the tornado chart. With the method I'm using to conduct the Monte Carlo, we can calculate other statistics, such as the chance of the value measure being below 5 or above 15. And what we find is that the chance of being below 5 is focused on the triangular and the exponential, whereas above 15, it's around exponential and the discrete. If you're interested in learning more about this Monte Carlo method, visit probabilitymanagement.org. You can read The Flaw of Averages by Sam Savage, and you can review my many YouTube channel videos that include videos around creating the tornado charts and other topics such as cost and schedule risk analysis. If you'd like a copy of the model, please contact me at brian@theputz.com, and I'd be happy to send it to you. Thank you for watching.